There's an iron that bends 90 degrees without cracking, while steel shatters at 15. Seismic testing at UC Berkeley proved wrought iron structures absorb earthquake energy instead of transmitting it through the frame. No welds, no joints, no failure points. Solid bars hammered into shape, grain by grain. The last forge closed in 1969. This is the story of the metal that earthquakes cannot break. Welcome to Lost Build Archives. The journey of wrought iron begins over 3,500 years ago in ancient Anatolia, where early metallurgists discovered how to extract and work iron into tools and weapons. While its origins were humble, this material would eventually revolutionize construction across the globe. By the medieval period, European blacksmiths had perfected techniques to create a remarkably resilient metal through countless hammer strikes and careful heating. The Industrial Revolution transformed wrought iron production with the introduction of the puddling process, a method that removed impurities and created a uniquely fibrous, slag-infused metal unlike anything we produce today. This wasn't just another building material, it was the backbone of 19th century infrastructure. The evidence of wrought iron's superiority still stands before us. The Eiffel Tower, completed in 1889, remains standing and flexible despite over 130 years of wind, weather, and structural stress. The Brooklyn Bridge, with its massive wrought iron cables installed in 1883, continues to carry thousands of vehicles daily, with its original components still in service. Across Europe, Victorian-era buildings constructed with wrought iron frames survived 2 world wars, including direct bombing campaigns that reduced modern structures to rubble. These aren't anomalies. They represent a forgotten standard, buildings designed to last not decades but centuries without replacement. Fast forward to 2018, when Dr. Sarah Johnson, a seismic engineer at UC Berkeley, noticed a disturbing pattern. Modern steel buildings were failing during moderate earthquakes at rates that defied computer models. Something wasn't adding up in our understanding of structural resilience. Dr. Johnson began an unorthodox research project collecting and testing salvaged wrought iron from 1800s buildings scheduled for demolition. What she discovered shocked the engineering community. These century-old metal samples demonstrated 400% greater ductility than modern structural steel. They absorbed energy rather than transferring it, a crucial property in earthquake-prone regions. Her published findings challenged fundamental assumptions in the construction industry. Buildings weren't supposed to last hundreds of years. Materials weren't supposed to improve with age. And most importantly, a discontinued Victorian-era metal shouldn't outperform our advanced modern alloys. To understand why wrought iron performs so differently from steel, we need to examine their microscopic structures. Wrought iron consists of long iron fibers interspersed with silicate slag inclusions, creating a wood-like grain that prevents catastrophic failure. When force is applied, these fibers can slide and flex without breaking. Modern steel, by contrast, has a uniform crystalline matrix that, while incredibly strong, tends to fracture cleanly once its yield point is exceeded. The performance differences are stark. While structural steel typically fails after bending just 15 degrees, genuine wrought iron can bend a full 90 degrees without cracking. Its tensile strength ranges from 40,000 to 50,000 pounds per square inch, lower than some steels but more than adequate for most building applications. Most remarkably, wrought iron demonstrates fatigue resistance approximately 10 times better than structural steel, meaning it can withstand repeated stresses without developing microfractures. The cost difference was significant. Wrought iron sold for $2 to $3 per pound in 1900 compared to steel at 30 cents per pound by 1920. But this price comparison ignores the most crucial factor: longevity. Properly maintained wrought iron structures regularly exceed 200 years of service life, while modern steel buildings are typically designed for just 50 to 75 years before major renovation or replacement becomes necessary. So why did we abandon a superior building material? The answer lies at the intersection of economics, regulation, and cultural programming. The global steel industry today represents a $2.5 trillion market dominated by mass production techniques that prioritize speed and volume over longevity. Wrought iron required skilled artisans working metal piece by piece, a process impossible to fully automate. When Andrew Carnegie and other steel magnates consolidated the American metal industry in the late 19th century, they systematically acquired and closed wrought iron producers to eliminate competition. Regulatory barriers soon followed. Modern building codes are written around steel specifications with standardized testing procedures that don't accommodate alternative materials. Structural engineers now graduate without any training in calculating loads for wrought iron components. The knowledge has been systematically erased from professional education. Financial systems reinforced this change. Insurance companies refuse coverage for buildings using obsolete materials not listed in modern specifications. Contractors cannot easily source components not listed in standard databases. And liability concerns make engineers hesitant to specify materials outside current code, regardless of their proven performance. Perhaps most effective was the cultural programming that steel is stronger, a half-truth repeated so often it became unquestionable. What this narrative conveniently omits is that raw strength is just one factor in structural resilience. Flexibility, fatigue resistance, and failure characteristics often matter more in real-world conditions. Despite this systematic suppression, wrought iron is experiencing a quiet vindication. UC Berkeley's seismic studies between 2018 and 2023 have conclusively demonstrated its superior performance during simulated earthquakes. MIT materials scientists have confirmed its exceptional ductility under stress. Even Japanese earthquake researchers, leaders in seismic safety, have validated the benefits of its flexibility compared to rigid modern alternatives. International recognition is growing. The United Kingdom now specifically requires wrought iron in heritage building restoration, acknowledging that modern substitutes don't match the original performance. New Zealand, situated on major fault lines, is considering wrought iron specifications for critical infrastructure in seismic zones. An underground movement of artisans preserves the knowledge that industry tried to erase. Blacksmith revival communities, historic preservation specialists, and dedicated metal workers continue producing true wrought iron using traditional methods. They maintain techniques passed down through generations, refusing to let this knowledge die. The success stories are impossible to ignore. Buildings that survived the 1906 San Francisco earthquake remain occupied today, their wrought iron frames intact despite a century of seismic activity. The Eiffel Tower, once planned as a temporary structure, has maintained its structural integrity with minimal maintenance for over 130 years. And the Brooklyn Bridge's original wrought iron cables continue carrying traffic daily with no signs of failure. For those interested in exploring this forgotten technology, practical pathways still exist. A handful of specialty suppliers still produce limited quantities of true wrought iron using traditional methods. Connecting with traditional blacksmiths can provide access to both materials and knowledge about working with them properly. Studying historic building techniques through preservation societies offers invaluable insight into pre-industrial construction methods that often outperform modern practices. Resources like the Artist Blacksmith Association archives provide technical documentation on wrought iron properties and working methods. Historic preservation engineering guides often include specifications for matching original wrought iron components. Materials testing laboratories can verify the authenticity and quality of salvaged or newly produced wrought iron. The legal considerations are complex but navigable. Most jurisdictions allow alternative materials permits with proper engineering documentation. Structural engineer approval is essential, requiring a professional willing to certify non-standard materials. Insurance coverage typically requires additional disclosure, but remains available for properly engineered structures. Community connections provide crucial support on this journey. Blacksmithing forums and guilds maintain living knowledge of traditional techniques. Historic building restoration networks connect property owners with specialists experienced in working with period-appropriate materials. The last wrought iron forge closed in 1969, but the knowledge lives in the metal still standing. These buildings represent more than just history. They embody a philosophy of construction focused on multi-generational durability rather than planned obsolescence. A metal that bends without breaking threatens an industry built on replacement cycles and continuous consumption. Perhaps this explains the systematic erasure of a technology that provided superior resilience at the cost of corporate profits. What shocked you most about wrought iron's forgotten legacy? Share below and help revive this knowledge. Subscribe now to preserve what they tried to make obsolete. The past holds the blueprint for our future.